In this video, I'm going to show you an example of building a custom AMI with Rocky Linux that's HPC ready and works with PCS. So this raises the question of why do we even need to do this in the first place? After all, isn't there some official PCS AMI that has everything on it? Well, it's not actually so simple, and here's why. So I'm a genomics and bioinformatics guy. You might be into CAE or weather modeling. I happen to prefer Ubuntu because it's similar to my desktop and my data science environment. You might prefer Red Hat or Rocky Linux because those are more enterprisey. And absolutely, let's not even get into what happens when we add ML frameworks into the mixture.
PCS is growing quickly, so we want you to know that if you see a message on your screen in YouTube here, there's a good chance that the video that you're watching right now has been replaced with a newer version. It might be a small change or a really big one, but either way, your life will be more pleasant if you watch the one that describes how PCS works today, not how it was in the past when we launched the service.
HPC environments end up being really bespoke. They are kind of precision tailored to fit the workloads and the user base that runs on them. So we decided when we designed PCS that you bring your own AMIs that either you build or somebody else builds and shares with you. Now, one potentially obvious question with this whole strategy is, what if I just want to kick the tires and I don't want to build an AMI? Well, we do provide a sample AMI, and that has Slurm, the PCS agent, and some basic system software installed on it. But we don't recommend that you use it for production work. Instead, we recommend that you take the reins and build your own AMIs, and I'm going to show you how to do that. So what does it actually take to build an AMI? So it's pretty straightforward, as you'll see in the building part of this video, but briefly, you launch an instance from a baseline AMI. Now this can be a base image from one of the supported operating systems, or it can be a golden AMI that's maintained by your organization. Then you add whatever you want to the AMI, additional applications, drivers, configurations, reference datasets, so on and so forth. And then, and this is the important part, you install the AWS PCS agent and the version of Slurm that's compatible with your PCS cluster. Finally, you create an AMI from the instance, and when it's ready, you tell PCS to use it in a compute node group. And that's it. So with that in mind, let's go ahead and get building. So I'm going to walk through building a real custom AMI that I can use with PCS. I've got 5 objectives with this AMI. So first, I'm going to use Rocky Linux 9. I've got other choices, but I'm going to use Rocky Linux. I'm going to optimize for AMD CPUs, and that's because my target compute architecture is the HPC-7A family. I'm going to support EFA and FSX for Lustre because this is an HPC workload. I'm going to make my AMI support CloudWatch and Systems Manager so that I can integrate with other AWS services, monitor, observe, etc. And critically, I'm going to use Spack to manage the user land software. And this will include installing OpenFOAM. With that said, let's go ahead and get started building the AMI. So to do that, we go to the EC2 console, and we need to launch an instance. Okay, so we go to the EC2 console, and we need to launch an instance, a build instance. So we'll choose launch instance, and we'll give it a name. Then we're going to go and search for Rocky Linux to find our AMI. You're going to notice you have 2 choices here. There are Rocky Linux distributions in the AWS Marketplace, and there are community AMIs. So the Marketplace is for folks who might want paid support from Rocky Linux. We're going to actually go with the Community Edition today. So we can find that one of 2 ways. We can kind of manually scan through the list. We're looking for the official owner for Rocky Linux. Their owner ID starts with 792. Or we can just search for another string, Rocky 9 EC2 base 9.4. We'll select the most recent x86 build if there's more than one. In this case, there's really only one that's here that we care about. So we've selected it. Now we have to pick our instance type. So if you're just going to install packages on your build instance, a smaller instance is okay. But if you're going to use Spack, if you're going to manually compile software, if you're going to do any real work on the instance that you're using to build your AMI, choose a larger instance because it needs a little extra juice. So I'm going to pick a C78 extra large, 32 vCPUs, 64 gigs of memory, plenty of juice. Who could need more than 64 gigs of memory? We'll pick our key pair so that we can log in. And now let's configure our network. So default will work just fine, but I like to actually switch into the VPC that I'm using to test PCS for various reasons. So there, we want a public subnet. One of our public subnets, let's go with US East 2B. We want to make sure to enable a public IP address, and we want to select a security group that allows incoming SSH. So it's important that we have SSH configured on this instance, and that's because System Manager isn't installed by default on a lot of third-party operating system AMIs. And that means if you don't have SSH configured, it'll be hard to get into the instance. So in this case, that's what we're doing here. Let's configure storage now. So we definitely need more than an 11 gig root volume. Let's go ahead and bump it up to 64 gigs. That should be enough room to start with. And since it's available, let's actually pick GP3. So GP3 is actually a little bit more performance, and it is also, counterintuitively, a bit more cost-effective than GP2. So we'll launch our instance, and in just a minute, we'll be able to find its public IP address. And once the instance has passed its status checks, we can comfortably log into it. But right now, it's currently initializing. It's been a couple minutes. Let's refresh. Okay, we can see that our status checks have passed. So let's go get the IP address for this instance. Okay, and we're going to hide the console. We won't be back to the console until it's time to actually build the AMI. So let's log into our instance. Here is the SSH key that I chose. Note the default username for Rocky Linux is Rocky, not EC2 user or root or CentOS. And we're in. Accept the key fingerprint, and here we are. First thing that I like to do when I'm building an AMI is update. I like to update the security patches, and then I have to reboot. So let's go ahead and kick this off, and then we'll talk a little bit about updating. We're going to do sudo yum update security y. What this means is only apply security-related patches, and don't just arbitrarily randomly update packages. And the y is don't prompt me, just go ahead and do it. So while this is cooking, you can skip this initial update. I like to do it to make sure that at least the security posture of my AMI is solid before I build something off of it. You can also choose to update everything. It'll take a little longer. A lot more will get updated, especially if it's been a little while since the AMI was built. You can also choose to skip just kernel updates. And I bring up kernel updates specifically for one reason, and that is Lustre. So it's not uncommon for Lustre support to lag behind the latest kernel release. And the outcome of that is you update your kernel, and suddenly the Lustre driver, Lustre system software is incompatible with your operating system, and you have to roll back, and it's just really frustrating. This is just one of the pain points that we live with. My advice here is be aware of what's going to get updated when you run yum update, and pay attention to what does get updated in case you have to troubleshoot, and just be aware of the potential impact for the downstream components of the things that you're going to install in your AMI later. Here we are. We need to reboot. Typing is not going well today. Okay, so this will take like a minute or so for the instance to reboot. Okay, let's log back in. All right, so the first thing we're going to do, I'm going to do all of the software installation as root. I'm going to make a software directory to put all of the downloadable assets in. And this is so that at the end, if you choose, you can delete all of these temporary assets really quickly. You don't have to go chasing them around in temp directories, etc. We're in the software directory. Let's go ahead and start by installing Lustre. I like to do this early because, as I mentioned earlier, it sometimes lags behind OS updates. Better to find out earlier that I'm going to have trouble than later after I've installed a bunch of other stuff. Just a reminder, the canonical docs for Lustre installation, especially for working with FSX Lustre, is in the FSX Lustre user guide. I'm just recapitulating the Rocky Linux steps specifically here. So basically, I need to add the FSX Lustre repo. So I import its signing key, and then I connect to the repo. So before I do the installation, I need to check the kernel version on my operating system. Remember what I said about Lustre and kernel versions? In the FSX user guide, there are special instructions for various kernel releases in Rocky. So uname R. So I'm running kernel 5.14.0-427. Luckily, lucky for you, lucky for me, we don't have to do anything special to install Lustre. So let's forge ahead and do that. This will take a couple of minutes. I'll say while this is going, at the end of all of this, if I wanted to, and if I had an FSX Lustre file system in the same VPC and the same availability zone as my build instance, I could actually test mounting an FSX Lustre file system just to be sure that things work. I'm totally confident that this is going to work. What's the worst that could happen? So I'm not going to do that, but you could. Okay, this scriptlet is taking a while to run. When I think scriptlet, I think little, I think fast, I think nimble. I don't think enough computing power to send a manned spaceship to the moon. Here we go, and we are ready. Okay, so we've installed Lustre. Now let's move on to the other main file system type that we often use in PCS HPC. That is EFS. So we recommend using EFS for shared home directories. And in fact, the PCS user guide and the getting started guide, we show you how to mount EFS. But when we do it, we demonstrate using EFS utils, which is something that's available in the Amazon Linux Extras repository. But here's the challenge. That's not directly available for third-party operating systems like Rocky Linux. You can still build EFS utils from source. It's totally open source. But honestly, it's a lot of trouble when all you have to do actually is treat the EFS volume like a native NFS mount and just mount it as an NFS type rather than an EFS type. Anyway, moving on. If we want to be sure that we're NFS ready, let's just make sure NFS utils are installed. They're installed. Okay, so we are EFS ready. Let's move on to EFA. We're building an HPC box. Obviously, we want EFA. Luckily, it's super easy to install. So we're in our software directory. Let's download the EFA installer. CD into the installer directory and run the EFA installer. Yes, don't prompt me. Okay, this is going to put a fair amount of stuff on the operating system, so this actually takes a couple of minutes to run. So if you've watched the video where we configure EFA to work with PCS, I reference building your own AMI, making sure the EFA software is installed on it. This is what I'm talking about. A default AMI won't work with EFA unless the software is installed and configured. So EFA is successfully installed along with OpenMPI 4 and 5. Now it's time to install SSM and CloudWatch agents. So these are optional. Some customers choose to install SSM and CloudWatch as part of their instance boot, the launch script. I don't like to do that because it adds latency and a chance for failure to my instance boot up, and I don't want that to happen. So I'm just going to embed them in the AMI. That way I don't have to worry about it. So in both cases, we're just going to install them directly from a URL. These are RPMs provided by Amazon. So there's the CloudWatch agent, and now the SSM agent. Now I'm going to do one other thing after I've installed the SSM agent, and I'm going to just check and make sure that the SSM process, I'm going to make sure that the SSM service is up and running. The reason I'm going to do this is I really want to be sure that when this AMI boots in future instantiations, in future instances, that SSM comes up. And so a quick way that I can kind of check that that will work is to make sure that nothing prevented the SSM agent from being installed, enabled, and configured to start by default. So it worked, it's okay, the service is running, it can't connect to anything, but that's totally okay. All right, clear our screen. So now it's time for the AWS PCS specific part of building our AMI. I usually recommend doing this last, but in this case, I'm going to install them after the system update and some of the basic software, but before I start working with Spack. And the reason is that the script that we use to install Spack likes to know where the Slurm install directory is so that it can integrate Spack and Slurm together. So first, we're going to start with the PCS agent. We're in our software directory. We're going to download it from our regionalized bucket. And we'll run the installer with yes to avoid prompting. This goes super fast. And that's because honestly, the PCS agent is super lightweight. All it really does is it's responsible for, when the instance boots up, phoning home to the PCS API, and then taking the information that it gets from that and configuring Slurm D to talk to the Slurm controller. Super lightweight. Okay, so now it's time to install Slurm. We need to install the version of Slurm that's compatible with PCS in our cluster. Easiest way, the most recommended way to do that is to use the Slurm software installer that Amazon provides for you. So that's what we're going to do. We're on our software directory. We will download from this regionalized bucket. CD into the bucket. Okay, so we'll run the installer for Slurm. This is actually going to take a few minutes. And the reason is we are actually compiling some dependencies and Slurm from source. Maybe someday this will speed up and be accomplished using binaries, but today we actually compile from source. So my estimate on a reasonably fast instance, this will take 5 to 7 minutes. Okay, Slurm has been installed. Let's just double check. You can find it in opt, AWS, PCS, scheduler, and there's Slurm and the source code. And you'll notice LiveJWT and PMEX have also been installed, but the key thing we care about is Slurm 2311. Okay. So we could stop here, and the AMI that you build will work perfectly fine with PCS, but it won't have any domain-specific software on it. And that's okay if you're going to do your software installation in a shared network directory. But I like to embed as much as I can, at least my compilers, my common libraries, my MPI, the heavy lifting part of my HPC environment in my AMI. So that's what I'm going to do. I don't feel like tracking all the dependencies down. I don't feel like installing a bunch of RPMs. So what I'm going to do is I'm going to use Spack. So we're going to install Spack, and we're going to use Spack to install a non-trivial HPC application and all of its dependencies. And it's going to take a little while, but it won't take anywhere near the time of doing this by hand. And you'll get a nice, flexible, usable HPC environment out of it. So before we get started with Spack, we've got 2 quick dependencies to add. One is going to be Git. We need Git because the installation method that we're going to use for Spack requires Git to check out the Spack repository. We're also going to install Screen. So I like to use Screen so that I have a terminal session that can't easily be interrupted. I can detach it, it can kick off and run in the background, my internet could go out, and there's no chance that the process is going to get interrupted. You can use any of the alternatives like tmux, but the point is these software installs can take a long time. You really don't want to have to start them again. That's just super irritating. So I recommend having something that lets you multiplex your terminal connection. So let's go ahead and do that. We'll just use DNF install screen and Git. It's the easiest thing we're going to do all day. Okay, so now we can go ahead and install Spack. You can follow the generic Spack installation instructions that you can find on their website and online, but we want additional compilers, optimized Spack configs, and access to the binary cache. So to get there, we're going to use a fork of the Spack installer that Steve Sachs from HPC Performance Engineering at Amazon maintains for Parallel Cluster. We've adapted it to support PCS. I've released it in its current form under the Spack for PCS recipe and HPC recipes. It's probably going to be updated in the future and merged into the mainline script that Stephen maintains. We'll keep you informed on how that's going. But right now, we're going to download that installer script from HPC recipes. So now the name of the file is install.sh. Let's make it executable. Launch an instance of Screen so that it can survive being detached. And now we're going to run the installer. So this installer is parameterizable. And we're going to tell it to use /opt as the install directory, which was going to result in /opt/Spack being where our Spack installation is. We're not going to install the Intel compiler because we're running on AMD instances. It doesn't make a huge amount of sense to do that. And we're going to set the Slurm directory to the one that's created by the PCS Slurm software installer. So here we go. So you can see it's checking out from GitHub. Actually, it's checking out from Git. I can tell you it's checking out from GitHub. That error is fine. Spack setup completed. Sounds pretty great. Okay, so we need to log out and log back in. And let's check out what Spack did. So the Spack installer that we use sets up etc profile D. So by default, users on the system should have access to all the various Spack binaries and configurations. So let's see if that's the case. So we'll do Spack help. Okay, so we know about Spack. We didn't have to manually add it to our path. Let's find out what's installed by default. Let's Spack find. Let's see, basically some build tools. I have a GCC 11.4 environment, a little bit more modern than what was used to compile Rocky Linux. So let's go ahead and configure something. Let's go ahead and install something with Spack. I'm going to choose OpenFOAM, which is pretty complicated to build from source and just honestly kind of excruciating because of how many dependencies it has, as much as I love OpenFOAM. Make sure that we're in a screen session. So let's find OpenFOAM. So you can go to Spack Packages website and just search for software that you want to install, but there's also an interface for it right on the command line. So Spack list, and then the keyword that you're searching for will give you the same interface as searching for it on the web. Spack list OpenFOAM, but there are like 8,000 packages. So the first time this runs, it takes a couple of seconds to cache. Okay, so we ran Spack list OpenFOAM. We can see that there are 2 packages that match OpenFOAM. There's OpenFOAM and openfoam.org. Let's find out what these are. So Spack info OpenFOAM. Again, this interface is information is identical to what you can find in Spack packages. So it looks like the OpenFOAM package is the professionally supported version available at openfoam.com. I'm assuming openfoam.org is the community version. Yes, OpenFOAM.org is the community version. So I'm going to go ahead and install the community version because that's what I'm the most familiar with. One of the great things about Spack is you could install both. You can install multiple versions, etc., etc., and Spack will just take care of all the dependencies. Spack install OpenFOAM.org. The ampersand basically tells us to install a version, and we want to install OpenFOAM Community Edition version 10. So let's wait, make sure this kicks off, and then we'll detach the screen and I will go and do some additional work away. Okay, welcome back. It's been about 35 minutes. We've installed OpenFOAM. Just reload our environment and let's see if OpenFOAM is successfully installed. Let's do Spack find OpenFOAM.org. Okay, there it is. Let's do Spack load OpenFOAM, and we don't have to have the version number there, but we will just for completion's sake. And now we should be able to lots of OpenFOAM environment variables. Sorry, echo. So there'll be lots of OpenFOAM specific environment variables that are set. We've loaded this module, and all of the OpenFOAM binaries will be in our path. So let's look for simple foam. There it is. Okay. All right. So let's go clean up our software directory. We can see it's 1.3 gigs. No sense keeping that on the hard drive. Okay. All right. So we're done here. Let's go back and actually build our AMI. So to do that, we're going to go back to the EC2 console and we'll go to our instance. Here's our Rocky 9 build instance. We're going to do actions, image and templates, create an image. So I'm calling it HPC Text Shorts, Rocky 9, x86-64, Slurm 2311, Spack. I'm going to put a date stamp on here. Theoretically, we could add a description. If we want to change the root volume size that this creates, we can set that here. I'm just going to leave it at 64 gigs. And we're going to kick off create image. This will probably take another 25 to 30 minutes. Okay, so it's been about 30 minutes. I'm back in the console, and let's go check our AMIs and see if our AMI has been built. There's a couple in there. That's because there's one that I built the other day. So here's the one that I just built. Its status is available. And so it should be ready to use with PCS. So let's go to the PCS console and create a compute node group with this particular AMI. All right, so we're going to go to our getting started cluster, put it in any cluster, doesn't really matter. We'll go to compute node groups. We could update one of these existing compute node groups to use our AMI, or we could create a new one. I'm going to create a new one because there's a specific instance type that we've targeted when we built this AMI. So let's create our node group, call it HPC-7A demo. We have a launch template prepared for it, a profile prepared for it. This is all stuff you've seen before. Instance types, HPC-7A, 96 large. Okay, so for scaling, when I'm testing out a new AMI, I like to start with a static scaling configuration that brings up an instance that's not going to go away. I can log into it, check that everything is working, and then I can go back and set my scaling to completely dynamic. So that's what I'm going to do. I'm just going to tell this to launch a single instance. Then we go and we pick our AMI. So your display will probably look a little bit different than mine. I'm internal to Amazon, so I'm going to have a lot of things that have been shared with me. But basically, you have two bits here. You have all the PCS sample AMIs, and then you have customer AMIs. And if we scroll down, here's the one that we just built, HPC Tech Shorts. Here's it's got the timestamp on it, so we know that that's the one we want. And we hit create. And in a couple of minutes, this node group will get created, and then it will, when the next scaling pass, it will launch a HPC-7A compute node. Our compute node group is active. We've set it to launch a single HPC-7A instance. We should be able to go find that instance in the EC2 console, connect to it using SSM, and we can do things to validate the instance, like make sure that Spack is installed, make sure that we can load Spack, make sure that we can load OpenFOAM, et cetera, et cetera. So we're not going to actually show that. It's a rehash of things that we've already done in other videos. But when you're sure that your node group is functional, your AMI is functional, come back to compute node group and set the scaling to be dynamic, the minimum instance count of 0 and a maximum instance count of whatever you want it to be, so that you're only using the instances that you want to. So what comes next? Well, to start with, we've just scratched the surface of what you can do with Spack. You could go learn about chaining Spack installations so that each user can have their own Spack in their own home directory, but it builds on the system Spack for all the basics like compilers and MPIs. You could also dig into multiple Spack environments. These can help you bundle sets of packages together, and this can be really helpful for creating domain-specific or use case-specific collections, like genomics, CFD, data processing, all available on one cluster, but not getting in each other's way. You could also find out how Spack and Anaconda can work together. This could help you support users that also need the Anaconda ecosystem, like data scientists and machine learning researchers. Finally, you could explore swapping out environment modules for LMOD. And this can be really helpful if you anticipate having a nested hierarchy of modules. Now on the operations front, you can keep building your AMIs manually, especially if you like to watch text scroll by on the screen. Your workflow can be as simple as keeping that build node around, waking it up when you need to make a change, and snapshotting a new AMI from it. Or you could lean into automation. Now, if that strikes your fancy, keep your eyes open for future blogs, videos, and HPC recipes where we'll start to show you how to progressively mechanize more and more of the maintenance of your PCS clusters.